good morning, everyone. My name is Rokicki, and today I will talk about designing RISC-V soft processor using speculative high-level synthesis. So this is a work which has been done in Rennes with Jean-Michel Gorius, Dylan Leoto, and Steven Doria. The context of this work is customizing your processor to your effective application. If you target an application where you need low power, you won't use the same microarchitecture or the same ISA that if we were targeting, let's say, a laptop or a smartphone. So you will want to customize your microarchitecture, so you can move from micro-coded processor, pipeline processor, multiple issue pipeline, or even out of order. But you also want to customize your ISA, so you may have more extension if you need more performances. So the goal of this work is to use high-level synthesis to automatically build a pipeline processor based on an instruction set simulator. So usually, if you want to customize your instruction set processor, you will have 3 different levels of abstractions. On one side, you have the instruction set specification. So for example, you can define all your instructions using building an ISS, instruction set simulator, which explains what all instruction does on your architecture. On the other hand, you have to describe the architecture, so you have to describe everything at the RTL level using Verilog or Chisel, for example. And sometimes, on the middle, you may use some domain-specific languages to describe the microarchitecture, so do you use a pipeline microarchitecture, do you need out of order, and so on. And most of the time, this domain-specific language can generate automatically RTL-level description of your hardware, but you do not have automatic microarchitecture inference. It means that based on a behavioral description of your instructions, you cannot generate automatically the microarchitecture. And most of the time, your domain-specific language for describing the microarchitecture is very low level, so you have to describe everything on your pipeline, you have to describe how you handle pipeline hazard, and so on. So what we want is to be able to write a simple instruction set simulator. So basically, in C, you will write a huge loop, which fetch an instruction, decode it, and depending on the opcode, do the correct thing on your architecture. So for example, if it's an addition, you will load registers from the register file, you will perform the addition, and you will write the result on the register file. And you want to use this simulator to feed it into a high-level synthesis tool and to obtain an efficient pipeline microarchitecture. So currently, it does not work because current tools are based on static scheduling, which cannot generate efficient pipelines for processors. So I will try to explain why it does not work, and I will start using a much simpler processor. So let's say that we have 2 instructions, so this processor can only execute branches or knobs. So here you fetch an instruction, and if it's a taken branch, then the next PC is the target of the branch. Otherwise, you just increment your PC. So you can translate this C code into your internal representation. So here it's quite simple. You have the fetch function, and then based on the instruction, you compute the target PC, and you have a multiplexer that decides the value of the next PC, either PC plus 1 or the target of the branch if it's a branch. And then you give this representation to your HLS tool, which will try to generate a pipeline. So it will first schedule the fetch, the resolve, it will increment and compute the target. But as it's a static, pessimistic schedule, you cannot start the next iteration until you know the effective value of the PC. So you will be able to schedule 1 instruction every 5 cycles. So it results of very poor performance, and it's not what you want. So using current HLS tools, you cannot synthesize an effective processor pipeline. So we've developed a transformation for HLS in Rennes, which is called speculative loop pipelining. And the idea is to modify your internal representation such that you can speculate on the outcome of a multiplexer. So you can speculate that the next iteration will start with PC plus 1. And you can start executing the second iteration using PC plus 1. And here you can see that we start a new iteration, a new instruction every cycle. And when we realize that we should have used the destination of the branch as a PC value, then we cancel everything that was computed with the wrong value, and we start again using the correct value. So this is exactly what you would do if you describe the pipeline manually. This is what you want to have in a CPU pipeline. So using this transformation, we are capable of generating the pipeline that we need. So a word about the transformation. So the idea, as I said, that you take a simple C code where you have an if statement which chooses between a slow pass and a fast pass. If you want to schedule this with HLS tool, we will have poor pipeline performance. But using our transformation, we are capable of generating a new C code, which is much more complex, difficult to read, but basically it has some rollback mechanism, some commit mechanism, a finite state machine for controlling everything. And if you give this new C code to existing commercial HLS tool, you will obtain exactly the schedule, the pipelines that you need. So if we go back to a full-scale RISC-V instruction set simulator, so we have the while loop, which with a huge switch case that decodes all the instructions of your ISA. It will translate again in the internal representation that we have. So we can see a first multiplexer here that is used to decide what is the next PC value, so either PC plus 4, or the result of a direct branch or a conditional branch. Then we have accesses to the register file in red here, and the values from the register file are used to compute either multiplication, something in the ALU, or memory access, and we have a second multiplexer here which chooses which value will be written back in the register file. So all of the multiplexers are opportunity to speculate for the next iteration and to generate an efficient pipeline. And once we have this representation, we can apply some automatic transformation on it to have different pipeline possibilities. So for example, we can transform the memory accesses on the register file, and we can insert some logic for interlocking. It means that we will add something that detects aliases between two consecutive iterations. So here, it will detect that one instruction uses the result of the previous instruction, and if we detect that, then we stall this pipeline for a few cycles until the result is ready, until the result is written in the register file. We can also automatically insert some forwarding mechanism, so we can have multiplexer which bypass the register file to prevent from stalling. So this can be inserted automatically on the pipeline, on the representation, and then we have more multiplexer, we have more opportunities to speculate and to generate pipelines that exploit them. And as everything is automated, we can also have automatic design space exploration. It means that we can configure the tool so that it cuts the multiplication unit into 2 parts or into 4 parts. And all the choice that we will do in the timing of the tool will lead to different pipeline organization, different trade-offs, and we can just try many different trade-offs to see which one are interesting or not. So we have a fully automated tool to generate pipelines based on this representation. And we can play with memory speculation, so interlocking or forwarding. We can play with different timing values. We can change the pipeline depth. And we can also handle the non-pipeline multi-cycle operations. So the results we have, so we synthesize 2 RISC-V processors. So one on the base instruction set and one with the multiplication unit. And the results are there. So vertically, you have the performance. So it's the time needed to compute a dry stone iteration. So the lowest is the better. And horizontally, you have the areas, so the size of the generated hardware. And for the base instruction set, we build the Pareto front. It means all the Pareto optimal configurations. It means that if you want the Pareto front, there is no other configuration that is faster without being bigger, sorry. So for the base instruction set, we can see that the orange points are points that we generate using our tool, and the other one are baselines. So 2 of the baselines are on the Pareto front. It means that we are not very good for the base instruction set to have performance. And that's because we had some expensive control logic, which is not optimized well, and which reduces the clock frequency of the design. And in the base instruction set, the control is on the critical path, so it affects a lot the performances. It's much better if we consider the multiplication unit, because now the critical path is on the multiplication path. And now all the points on the parameter front are points that we generate using our tools. So we compare against CVE4 and Comet, which is another core synthesized with HLS. And here we can see that some of the points we generate, so the fourth one, for example, is 36% faster than the CVE4, but we also have many points that are smaller with similar performances. So the conclusion is that as we generate multiple different points with different timing information, we are capable of finding interesting points and to find something that fits your needs. We can also add some custom instruction which will be generated and integrated in the pipeline automatically. So I was quite fast. So to conclude, we have a tool that is able to synthesize instruction pipeline automatically based on behavioral description of what your instruction will do. We can play with memory speculation automatically. We can play with different timing information. We can explore different pipeline organization automatically. And we can even handle multi-cycle operations. And the performance and area, even if it could be improved with some work, it's competitive. As future work, we plan to try to synthesize more powerful architecture, microarchitecture. So maybe if we unroll the main loop, we can generate superscalar processors. So we will fetch multiple instructions each cycle and commit multiple instructions each cycle. And we have to think on how to integrate out of order in our design. So can we synthesize automatically out of order microarchitecture based on description of the ISA? So if you want to discuss, I had a poster yesterday, so it's too late. Otherwise, you can send me an email. Thank you.
Thank you very much, Simon. Any questions for Simon? Huh? Simon, can I ask you one thing then? You've done all this. A lot of modern designs, we worry about formally verifying they're correct. Have you looked at how you might incorporate formal verification within your flow?
Yeah, we have plans to add some model checking to verify that everything that is committed in the generated pipeline would be committed in the first instruction set simulator, that we do not commit wrong instructions, that we do not miss some instruction, and so on. So we can add formal paths which will be generated automatically to have some translation validation that everything is correct.
Okay. Okay, I'll give you a second question then, which is the interaction between your design and the compiler toolchain, because compiler toolchains can have microarchitecture models that model the pipeline. Have you started to explore the interaction between the two of those?
Not really, but one interesting thing that we have, I did not speak about that, is that if we go back to the overview of the transformation, we see that if we give instruction set simulator, so a functional simulator of the ISA, what is generated by the tool is another C code, which is actually a cycle-accurate simulator of the microarchitecture that you will have. So you can estimate the performance accurately at the C level, so you may explore all the performance trade-off at the C level, which is much faster than hardware simulation.
Okay.
I think there is a question.
We have a question, yes, at the back. Jessica.
So speculation has been instrumental in getting modern processor performance, but it's also been instrumental in a whole host of speculation vulnerabilities. So if we're automating the insertion of speculation, how can I, as a designer, reason about and constrain the kinds of speculative attacks that I could be vulnerable to in my design?
Okay, so if I get the question correctly, you're questioning about security issues of speculation? Yeah? Okay, so actually the goal is to generate what you would do manually on a processor. So if you have issues with speculation on your microarchitecture manually, you may have the same on what we generate. But as we have a more formal, higher level model of the microarchitecture, maybe we will have more tools to reason about the problems and how to find mitigations. But yeah, it's a bit far for us. But that's planned of future work when we will start dealing with out of order and speculation at another level. Thank you.
Okay, thank you very much, Simon.